Hi, Professor Good. Give me one quick second. All right, can you hear me?
Yes, I can hear you. How are you?
Good. How are you?
I'm well, thank you. Let's check the focus. How does the focus look?
It looks good.
All right. What can I help you with tonight?
So today I just wanted to review circuits, and interval notation. Yes, starting off.
Okay. So circuits, and this is section 2.4.
Yep.
There are three aspects to circuits. All right. We have a circuit. We have a Boolean expression that tells us when the circuit is going to output a one or a hot wire, or we say makes the circuit light up. And exactly when those expressions run through the circuit, the output should be one. And then there is an IO table, which is sort of like a truth table for the Boolean expression. Oh, this should be Boolean expressions. The Boolean expression has P's and Q's and R's and ands and ors and nots, just like a statement form does. And we know that those statement forms are associated with truth tables. Well, Boolean expressions are associated with IO tables. And we want to be able to get from each of these to each of the other two, no matter what we're given. And one is true, and that's a hot wire. O is equivalent to false, and we think of that as a cold wire. And hot means, there's electricity running through it. And cold wire means there's no what we call juice or electricity running through it. Okay. Hey, Abu.
Okay.
So we're reviewing circuits.
Yeah, yeah, sí.
Okay. So, for example, we might be given the Boolean expression and we might be asked to draw the circuit for this Boolean expression. And it'll just be some expression that's well formed with P's and Q's. And, if we want three inputs, it could be R. So P and Q and not R, or P and not Q and R, for example. So the inputs are the P, the Q, and the R. So we line those up on the left because we always draw a circuit to read from left to right. So these are our inputs. And somewhere out here, we're going to have an output S. And that's going to be a wire that's either hot or cold. We only want it to be hot when either P and Q and not R come through the circuit, or P and not Q and R come through the circuit. Well, what does that mean? It means If the P wire, when we just write P, we're saying P is true. Here, that means P is a hot wire and Q is hot or true, and not R is true, which means R is false or cold. So if P is hot and Q is hot and R is cold, we want the output to be hot or true or 1. And if P is hot and Q is cold and R is hot, if that's the input state, all these together are called the input state, then we want a 1 or a hot output. If anything else comes through, we don't want to have a hot output. So we just draw the gates that describe this expression. So we work inside parentheses because we're constructing. So let's work inside this parentheses. We want to AND together a P wire with a Q wire, and we also want to run a not R wire all through one AND gate because we can build one AND gate that can accept more than two wires. An AND gate can accept two or three or four wires, just depends. So we can run P right into the AND gate. We're going to run Q right into the AND gate. So I'll draw from this Q wire with a solder dot, and I'll just bend it, and it can go in the AND gate. And we want a not R. So we're going to start with our R, but we're going to build a not gate. And that's not R now on this wire, and we'll feed that through that AND gate. So we have P and Q and not R, and this is the output from that AND gate. We'll deal with the OR last because it's the last operator. Here, inside this parentheses, the input state is P and not Q and R. Well, we don't have a not Q yet, so we can build a not gate for the Q. We have a P wire, so we can just draw from it and bend it. We don't need a solder dot to bend it. And we don't want not R, we just want plain old R. So we can pull from the R before it went through the not gate and just bend that. But we'll make our solder dots here to indicate that this is where the wires are touching. When wires just cross without a solder dot, like here and here and here, they're not touching. And we'll run these through the second AND gate. And we always put the names inside the AND gates and the OR gates because they look a lot alike. So here's this AND wire, and here's this AND wire. And then we've got this built and this built. The last thing to do is run these two wires through this OR gate. So we're just going to bend them so they're sort of symmetric, and we can put this through an OR gate. And that's the circuit for that Boolean expression. Does that make sense?
Yeah, it does. I'm just writing it down.
Uh-huh. So this can be, part A to draw the circuit. Well, part B is to construct the I/O table. For the Boolean expression and the circuit. And so this is when we remember, okay, we've got three different input variables, a P, a Q, and an R. So we'll need a column for P, a column for Q, a column for R. And our output column is S right there. Now, because we have three inputs, we're going to have 8 rows. Because we have two choices for P, it can be a 1 or an O, because it can be a hot or a cold wire. Same for Q, same for R. So we have 2 times 2 times 2, or 8 different possibilities for the input wires. For example, they could all be hot. In fact, it's easier to fill it in vertically because we know in a truth table, under the first variable, we would write true, 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 false, 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 false if it was going to be an 8-row situation. So we can write 1, 1, 1, 1, O, 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 O. then 1, 1, 0, 0, 1, 1, 0, 0, then 1, 0, 1, 0, 1, 0, 1, 0. And we can put a little horizontal line through there, so settle our I down. And what we need to understand is that each of these rows with this input represents a certain kind of situation with our input wires. For example, in row 1, P is a 1, it's hot, Q is 1, so it's hot or true, and R is 1. So this first row represents P and Q and R. But that's not part of the expression. See, neither of these two expressions is P and Q and R. In other words, we don't want a hot output when P and Q and R are all hot, because we only want a hot output in this circumstance or this input state. So the output in this row is O. Can you tell me what the Boolean expression is for the second row?
P, Q, not R.
Yeah, it's P because it's hot, and Q because Q is hot, and well, R is cold, but that means not R is what's hot. We always write what's true or what's hot to label the input. Well, P and Q and not R, that's one of the expressions that this circuit is going to yield hot output for, right? Because if P is 1 and Q is 1 and R is O, the 1 is coming into this AND gate. The Q is a 1, that's coming in. The R is an O, but when the O goes through the NOT gate, it flips it to a 1. So this wire coming in is a 1. And the AND is going to be outputting a true or a 1 when all of the input wires are 1. That's the way AND works. It only outputs a hot wire if all of the input wires are hot or true, because that's just the way AND works. Well, we will get a 1 here if P is 1, Q is 1, and R is O, because remember that NOT gate flips that O to a 1. So we'll get a 1 if P is 1, Q is 1, and R is O. Then what's coming in here is a 1, a 1, and a 1, and that's going to output a 1. Well, it doesn't really matter what's coming in on this bottom wire. If a 1 is running into an OR gate, that's enough to light up the output on the OR. And that's why we want to get a 1 in the second row. Jessica, do you know how to label this third row where P is 1, Q is O, and R is 1?
I mean, one quick second, I'm just still writing everything down.
Okay, I can wait a minute. Can you stop writing what you're writing and just answer the question?
So it looks like it's going to be P and Q,
But Q is
or
O.
P and not Q,
Uh-huh,
and R.
that's right. Is that one of the expressions that's supposed to yield a hot output?
It's the right one.
Uh-huh, because if
And
we put P
mm,
is 1 and Q is O and R is 1, when we run these wires through this bottom gate, here's the P wire, it's still a 1. The Q is O, but when the O goes through this NOT gate, it flips to a 1. And the R is a 1 right here. When we pull it through, it's still a 1. So we have 3 ones coming through this AND gate, and that output will be a 1. Doesn't matter what's going on up here. In fact, an O will come out up here, but that doesn't matter. We can write it, but it's not going to matter because O ORed with 1 is still a 1, and we'll get a 1 here. Here, I'll scooch this over and Put
And then
the
I got one on my side too.
good. These should be the only two rows where we get a 1 for the output because we've already hit the two expressions that were listed here in the disjunctive normal form. This is called disjunctive normal form, and it's really nice because it's really easy to construct the IO table without even ever drawing the circuit because we just read these expressions and we look for the rows where those expressions show up. And those are the rows where we know we want hot output. In fact, for row 4, this row right below the row we just did, what is the Boolean expression for that row?
For the last row, correct?
The fourth row.
The fourth one is gonna be P and not Q and not R.
That's correct. So this row is P and not Q and not R. And of course, that's not one of our expressions. So this output will be an O. What about the fifth row? What's the expression for the fifth row?
Not P and Q and R.
Good. And what should the output be for that row?
Give me 1 second. I'm just looking.
Is
Going
it
to
I?
be 0.
Yeah, because we don't have it
Yep,
here
because
or
we don't
there.
have those in the expression.
And in fact, now, just for good practice, we can write the Boolean expressions for these other three rows just for practice, because you never really know what you're going to get on a test. You need to understand the general idea. So let's go ahead and write these last three Boolean expressions, but we know that the output's going to be O for all of those because we already found the two ones. What's this row 6 expression going to be?
Not P and Q and not R.
Good. And what's the expression for the seventh row going to be?
Not P and not Q and R.
Great. And what is the expression for the very last row?
Not P and not Q and not R.
Uh-huh. And that would be when all of the inputs were cold or O's, but we don't have that as part of this circuit, so it's not going to light up the circuit. Now, it might be that you're simply given the IO table and asked to write the Boolean expression and draw the circuit. So let's do part of that. And then do review the class notes because we did a bunch of examples in class notes. All right. And on the test, review your test. I think I gave you an easy one that only had P's and Q's, right? I mean, those only had 4 rows. So here, um, draw the IO table or construct, either way, and the circuit associated with this Boolean expression. Excuse me, I want to give you the IO table. So I'm going to say, sorry, construct the Boolean expression. See, I want to play the game the other way. And the circuit associated with this IO table. Sorry about that. Can you see it?
I can see it.
Can you see it, Abu? Sorry about that. All right, so here we go. Well, I'm just going to give you one that's just got P, Q, and S. Okay, so when we only have P, Q, and S, then it's 1, 1, 0, 0, 1010 because we only have P and Q for our inputs. We only have two inputs, so it's only four rows. Now, I could put a variety of things here, right? But I'm going to put an O, a 1, a 1, and an O. So now we have to figure out the Boolean expression for this IO table. So it goes back to being able to read the input states that have the hot outputs because those are the input states that we want to use to build our Boolean expression. Does that make sense?
Makes sense.
So if we call these rows 1, 2, 3, and 4, which are the rows that we need to write the Boolean expressions for?
Would it be the first two? It
Uh,
wouldn't be all, right?
Look at the output. Remember, our Boolean expression tells us when we're going to get hot output. We got hot output in the row where the input was P and Q and not R. Okay, that was row 2, P and Q and not R. Or the row where we have P and not Q and R. And that was the third row, P and not Q and R. Those were the only rows where we have hot output because those are the rows that are described by the expressions inside the parentheses, and the whole thing is our Boolean expression. But each of these are kind of smaller Boolean expressions, you see. So this tells us where they're going to be ones. And that's in the output column. See, we only had a 1 here and here to go with this and that Boolean expression.
So are
So
we gonna
now
want the ones with the ones in them
the ones in the
in the
output
output? So it's gonna be two and
column.
three column or
That's right. So
two and
what
three.
is the Boolean expression for the input in, say, row 2? Because it's got a 1.
It's going to be P and not Q.
Good.
And
What?
then row three is going to be not P and Q.
And so the point is, if our input is P and not Q, or if our input is not P and Q, those are the times we want to get a 1. So we connect these row expressions with an or, because if this happens, P and not Q, or if this happens, not P and Q, those are the instances where we are going to get hot output, and that's it. We connect them with an or. So that's our Boolean expression. See, across the row, we use ands because we want P to be hot and Q to be cold. We want them to happen at the same time. When we connect rows going down, we connect those expressions with ors. Because if this happens in row 2, or if the input of row 3 happens, those are the times when we want ones for our output. So it's ands inside the parentheses and ors between the expressions in the parentheses. Does that make sense?
Just to make sure, so can you just go over one more time? So the or is because
If this happens, if P is
mhm,
hot and Q is cold,
gotcha, because they're opposite.
or if P is cold and Q is
Gotcha.
hot.
Either or.
So if this happens or that happens. See, the inside parentheses is what we call a complete input state. It's complete information about the input wires.
Okay. Would it ever be a situation where let's say it would be P and not Q and the other would be P and Q? In that case, would we put an and symbol in between? Or we still use or?
In WebAssign, you'll see problems of that ilk where it might not be in disjunctive normal form.
Hmm.
But again, when we have the expressions inside the parentheses giving us information about all the input variables. Here, there are only two, but in our first example, we had three, and inside parentheses, we're getting information about all three input wires, you see. And then when those parentheses expressions are called parenthetic expressions are connected with an or, it means if this is the input or if this is the input, we want hot output.
Gotcha.
Okay. So, for the circuit, we only have two input variables. So we only need a P and a Q, see, because we only have two input wires. We're still just going to have the one output wire, S. So let's see, we want to build P and not Q. So that means we need a not Q to run through an AND gate with P. We always label that with an AND so we can tell it apart from an OR. The other expression is not P and Q. So we need a not P so we can bring down here, draw from the P and run that P through a not. So now this is a not P. And we need a Q wire so we can bring it around here. And this AND gate is going to light up when P is cold because this wire will then be hot coming in, and of course when Q is hot. And then these get connected with an OR gate because the OR is the last gate. That's the other beauty of disjunctive normal form. You can kind of line your gates up. You know the last gate is always going to be the OR gate, whether, you know, it's got, two wires coming through it. It could have a bunch of wires coming in it. But then the gates before that are the AND gates, and the first gates are the NOT gates when you need them. Let me give you a do later, okay?
Okay.
So construct the Boolean expression and circuit associated with this IO table. And I'm going to make it with three variables. There's going to be a P, a Q, and an R for inputs. There's always just one output. So under P, I'll put 1, 1, 1, 1, O, 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 O. Just like if it was a truth table, ones are like trues, O's are like falses. 1, 1, O, O, 1, 1, O, O, 1, O, 1, O, 1, O, 1, O. And now it's my choice because I'm just making up an example, right? To figure out where I want to put the ones under S. So why don't you help me? We'll call this row 1, 2, 3, 4, 5, 6, 7, 8. Let's pick 3 rows to put a 1 in the output column S. You help me decide which rows we want a 1 in. We're just making an example. See, there are 8 rows. There are 8, choose 3 different ways to pick 3 of these rows to have the 1, and the rest would have O's. Because 8 choose 3 means how many ways can we pick 3 of these rows when we have 8 of them? So you tell me what rows you want to have your 1 in your output column.
And they could be any number of rows or any rows, any
Any
three.
rows, just pick 3. I just didn't want to make it too
Two,
big.
4, and 6.
Okay, 2, 4, and 6. And then you should be able to write the Boolean expression for these rows. And once you have the Boolean expression, you should be able to draw the circuit. But because we have 3 ones, this OR is going to have 3 wires coming into it because there will be three AND gates. There'll be an AND gate for this row, an AND gate for this row, and an AND gate for that row. Does that make sense?
Makes sense.
Good. All right, it's Abu's turn to ask a question. Abu, what can I do for you tonight?
I'm just sitting in. So, if anything, it'll just be about the WebAssign
All right, which WebAssign are you looking at right now?
7.2.
7.2.
Yeah.
All right, let me share my screen and let's look at WebAssign 7.2. Which one would you like to start with?
Could be number one.
All right, so this is talking about the properties of a function. And it says, well, you read the directions for me.
Uh, Filling each line with the word most or least.
Okay. Now, do you have your section 7.2 class notes open to help you?
Yeah.
Great. So this first one is about a function being one-to-one. Do you remember in your own mind what one-to-one means in terms of arrows? If we draw the arrow diagram, shall we go back and review the class notes together? Let's just look at the class notes. Let's just peek at them.
Coming out. Just checking out.
All right, so this was review of the definition of function, but then we had the definition of onto and one-to-one. So a function is onto if every element y in B appears as the image of some x and a, and some means at least one. In other words, if every y in B gets hit by at least one arrow. In other words, the range is all of B. Every Y and B gets hit with at least one arrow. That's what onto. Remember, onto means the arrows cover up B, the codomain, like a wall-to-wall carpet is completely onto the floor. Now, F is one-to-one if f of x1 equaling f of x2 means x1 equals x2. In other words, no Y in B gets hit with more than one arrow. We don't want two different X's to hit the same Y. So when we look at this first example, is it one-to-one? Do you remember?
Hmm. You say on the class notes. And you say this diagram right here?
Yeah, is it one-to-one?
No.
Why not?
So one to one, doesn't that mean that every element in the codomain should be should have an arrow pointed to it?
No, that's onto.
Okay. So
Onto means the arrows are completely covering up B, like carpet is onto the floor. Right? But one-to-one means you cannot have you can't have two arrows pointing to the same point in the codomain. See, A maps to R, D also maps to R, so F of A equals F of D because they're both equal to R, but A isn't equal to D. So, F of A, so X1 is like our A, is equal to f of d, x2 is our d, but this requirement that A has to equal D isn't true because A is not the same point as D. So 1-to-1 means each of these can have at most one arrow hitting it. Onto means each of these must have at least one arrow hitting it. Let's look at some other examples. Let's look at this arrow diagram. Is it 1-to-1? Does each element in the codomain have at most one arrow hitting it?
Yes.
Is it onto? Does each element of B have at least one arrow hitting it?
No.
No. So it is 1-to-1 because there's at most one arrow hitting everything, but that doesn't mean everything got hit. It just means if it got hit, it only got hit by one arrow at most. But it wasn't onto because 7 didn't get hit at all. If we look at, well, you can, we didn't draw the arrow diagram here, for example, 3, but you can just look at the ordered pairs. Look at the codomain. It's 2, 4, 6, 8. And now look at these ordered pairs. So we look at the second coordinates. Is H onto Y? Did every element of Y appear as the second coordinate at least once? Yeah, so if we drew the arrow diagram, it would cover up Y. So it is onto. Is it 1-to-1? In other words, did each of these codomain elements appear at most once as a second coordinate?
Wait.
Did each element of the codomain Y appear at most
Oh,
once?
no. No. 8.
Because 4 and 5 both hit 8, but 4 isn't equal to 5. So it's not 1-to-1 because h of 4 equals h of 5, but 4 isn't equal to 5. So you could draw the arrow diagram if it helps you, okay? So now if we go back to this problem, it says a function is 1-to-1. You read this and tell me what to say.
Function f is 1-to-1 if and only if each element in the codomain of f is the image of at least one element. Each element in the codomain.
Well, maybe we'll do the other one first. A function f is onto if and only if each element in the codomain, right, the codomain, is the image of, that means has an arrow pointing at it, of
least.
at least. And that means this one is at most, because you don't want more than one arrow coming out of the domain and hitting each element, some element more than once. Does that make sense? Okay. Now, here you read the directions.
But two of the following statements are correct ways to express the fact that a function f is onto. Select the two that are incorrect. So, f is onto. Oh, this of some elements in its to the that was known as domain as Man. So the second and the fourth one.
That's right, because the second and the fourth are actually the definition of a function, not the definition of onto. Good job. The other three are the definition of onto. Good work. So we have two functions, f and g, and they've just given us pictures, which is kind of fun.
Yeah.
I mean, yeah, okay. So is f 1 to 1?
Mm. So I can take this choice. No,
Okay, why not?
because C and D are pointing to E, are mapped to E in the codomain.
Uh-huh.
Oh, I gotta look at that. Fine.
So which one of these is saying that that C and D are both pointing to E, but C and D are different?
Oh, the last one.
That's right. Is F onto?
Uh, yes.
Yeah. And I'm sure you can figure out which of these is telling you why it's onto. Do you feel confident you can pick the correct answer there?
Could we
Why?
go over it actually, just to make sure?
Okay, I'm going to let Abu explain it to you.
Well, which one?
Is F onto?
Okay, so F, yes, F is on to because every element in the domain is has an arrow pointed to it.
You mean every element in the codomain.
Oh, yeah, in the codomain, in the Y.
So F is onto, Jessica, because every element over here in the target, which is called the codomain, is hit by an arrow. In other words, every element of Y is the image of at least one element back here in X.
Gotcha.
So let's see. Let's see which of these five statements is the correct explanation for why F is onto. Do you want to read the first one, Jessica?
Yup. So is F onto F is onto we're doing A, correct? Or which
Yeah.
one are we doing?
Yeah, you want me to
Okay.
F is you want me to
Oh,
highlight
F
it?
is onto because each element of Y is the image of some element of X. F is on. Oh, go ahead.
Uh-huh. So that's one answer. What
F is
about the
onto
second one?
because G is in Y, but G does not equal F of X for any element X in X.
But wait a minute. Look at G. Isn't it equal to F of B?
It is.
So we know the second one isn't right.
Yeah, so that's one. And then the next one is F is onto because no elements of X are sent by F to the same element of Y, and that's wrong, right?
That's good. What about D?
F is onto because every element of X is sent by F to an element of Y, and that's correct.
That's, see, that's the correct wrong answer. That is the most likely wrong answer because this is actually, it's easy to confuse onto with function.
Does
This,
every element.
this is actually the definition of a function. F is a function because every element of the domain X is sent by F to a codomain element. That is why F is a function, but that's not why it's onto.
Okay.
It's onto because every element of Y is hit by an arrow. And the way we say that is every element of Y is the image of some element of X. So getting hit by an arrow means, E is getting hit by an arrow. It is the image of both C and D. So it definitely gets hit. F is the image of an element of X. What is F the image of? Little f, this element, right? What is this little f the image
It's the
of?
image of A,
Uh-huh, great. See, now you're learning the language. And what about G? Is it the image of an element of
of
X?
B,
Yeah.
and
So
F is the image of your A, and then E is the image of C and D.
so every element in Y
Okay.
is the
Onto.
image of
It's hit
some
by an
element of
arrow.
X. That's what it means to be onto. This
Okay.
other thing is what it means to be a function. See, the first statement says everything in Y gets hit by an arrow. The fourth statement says every element of X has an arrow coming out of it. F is a function. It should say function because every element of X is sent by F to an element of Y. That's what's required for a function to be a function. Okay. What about G? Is G one-to-one?
Uh, no,
No. Why is G not one-to-one? Just tell us with your own words, Abu.
F is an image of A and B, and A is not equal to B.
That's right. It's also the image of D, I think.
Oh, yes.
So it fails to be one-to-one triply. It's like a triple loser. But I think they picked A and B, but A isn't equal to B. Is it onto? Is G onto? Did every element of Y, is every element of Y the image of some element back in the domain X?
No.
No. Which element of Y didn't get
G.
hit? G. Yeah. So you can figure out which of these is saying uh that G is not onto. And so here's just another one to practice with, okay? This is a little function from Z to Z. It's a simple linear function. The domain is the integers, and we're mapping to the integers. And I just want you to just follow through the algebra. It turns out that every linear function is one-to-one. Now remember what the definition of one-to-one is. And you need this definition that if f of x1 equals f of x2, if the y values are the same, that's what this says, then x1 equals x2, okay? That's the definition of one-to-one you want to hold in your mind, okay? So here it says, is f one-to-one? Well, it says, suppose n1 and n2 are any integers such that f of n1 equals f of n2. Now, why are they saying that? Because that's the hypothesis for one-to-one, that f of one element equals f of another element. See what I mean? So this argument that we're going to walk through starts with the hypothesis of one-to-one, that f of one element equals f of another element. The elements aren't called x1 and x2, they're called n1 and n2 because they're integers instead of real numbers. See, I mean, they're real, but they're integers. So we're assuming that f of n1 equals f of n2. Now let me ask you this. If it turns out that we're going to prove f is one-to-one, what would we wish to show? Look at our definition.
The conclusion, x1 equals x.
That's right. And the conclusion here would be that n1 equals n2 because we're using n instead of x. Does that make sense?
Yeah. So, Professor, on the definition you just had up just now, uh,
Uh-huh.
where you had f1, so this where you have f of x1 equals f of x2, implies, would that be correct to say implies?
Uh-huh.
Okay, so x1 equals x2. So this f of x, is that the codomain or?
Yeah. F of x is the y value. The ordered pair, x, y,
Mm,
well, y is the f of x. So we could write this ordered pair x comma f of x because y is equal to f of x. Y is the image of x under f. Okay, the second coordinate is the f of x value. Does that make sense?
okay, yes. So they so they be so they started with that one with the codomain on that
Yeah, they started with the hypothesis of the definition of one-to-one. We're assuming f of x1 equals f of x2. We're calling it f of n1 and f of n2, but we're assuming those are equal. So we're gonna try to prove this if-then statement directly. We're gonna assume the hypothesis, and then we're gonna see if we can prove the conclusion using algebra and the definition of f. So let's go and look at this. In fact, do you have the same function I do, 2 minus 3n?
then it's
What's your function look like?
hold two. Oh, okay. We have, yeah, 2 minus 3 and yes,
All right, all right, I want to just show this to you. What number was that?
it's number 5A.
So f is a function from z to z is defined by f of n is equal to 2 minus 3n. Is that it? Is that it?
Yes.
For every, n in Z, and here we're viewing Z as the domain. Okay, so here's the domain, here's the codomain. So, we drop in a domain element. and then out comes the codomain element, f of n. That's our y, okay? So you can think about it as my little monkey grinder, right? Where you drop in an element n from z, and out comes 2 minus 3n, which is also in z, right? Because differences in products of integers are integers, right? So you can think about it as an input-output situation if you like. So the point is to prove f is 1-to-1, we must show that f of n1 equals f of n2, that implies that n1 equals n2. In other words, if f of n1 equals f of n2, then in fact n1 had to be equal to n2 to begin with. Okay? So we assume f of n1 equals f of n2. And let's see if we can prove that n1 equals n2. We have to use the definition of f, of course. We have to use the definition. That voice is still haunting us. But the definition is simple. It just means if you're dropping in n1, then out comes 2 minus 3 n1. So this is 2 minus 3 n1 equals 2 minus what? Well, if we're dropping n1, out comes 2 minus 3 n1, okay? But if we drop in n2, what comes out?
2 minus 3 and 2.
Exactly. So that's what it means to say f of n1 equals f of n2. It means their function values are equal. Does that make sense? We're just using the definition of f of n here and here. We started with this. We started with assuming that f of n1 equals f of n2. So the definition of f tells us 2 minus 3 n1 has to equal 2 minus 3 n2. I mean, that's what f is. Okay, now we can subtract 2 from both sides of the equation, right? And we're left with minus 3 n1 equals minus 3 n2, right? And now we can multiply both sides by negative 1/3. That's perfectly legal. As long as we do it to both sides, right? It's legal. So the negative 1/3 cancels with the negative 3. And lo and behold, n1 equals n2.
And if can we divide by negative?
Sure. Like if you have negative 3 n1 equals negative 3 n2, you can divide both sides by negative 3, and it's the same result. See, multiplying by negative 1/3, if we take x and multiply by negative 1/3, that's the same thing as taking x and dividing it by negative 3, because x over negative 3 is x over 1 times negative 1/3. That's what dividing by negative 3 is. We're actually multiplying by negative 1/3. Multiplying and dividing are two sides of the same arithmetic coin. Did you know that?
Not really.
What?
Not really, no, I didn't.
Well, I'm glad you know it now.
My first instinct would have been to just, divide. I would have never thought anything about it.
Right. Well, maybe it's a good thing I showed you both ways.
Hmm.
Because when we're dividing, we're really multiplying by the reciprocal,
Makes sense, yes.
right? Dividing x by y is the same as multiplying x by 1 over y. Because x is x over 1.
Okay, yeah.
And when we multiply two fractions, we multiply bikini style, right? Multiply the tops, multiply the bottoms. It turns out that any linear function is one-to-one. It's like the classic case of a one-to-one function. So in general, any linear function is one-to-one. So what do I mean by linear function? F of n equals, well, the general formula for a line is some coefficient times n, but n is always just to the first power. That's what makes it linear, plus a constant b. Here, a and b are real. Or if we're playing integer games, a and b are integers. And I think here we're playing integer games. But this is a linear function. A quadratic function, I'm sure you've heard that phrase, right? It looks like this. F of n equals a n squared plus b n plus c, right? And then a cubic function, these are all polynomials. Well, that's f of n equals a n cubed plus b n squared plus c n plus d. See what I mean? It's the highest power of n that tells you the name. So if the highest power of the variable n is 1, it's called linear. Anyway, any linear function, this is just an aside, okay? You don't need to, go off the deep end. I'm not going to give you one of these, okay? But any linear function is one-to-one. Why? Let f of n1 equal f of n2. See, it doesn't matter what these numbers are. So a n1 plus b equals a n2 plus b. And then we're back to the same process. Subtract b from both sides. They go away. Then we have a n1 equals a n2. Divide both sides by a, assuming a is not equal to 0, of course. And n1 always equals n2. So every linear function is always one-to-one. Now, I'm going to leave you with this thought. We had this function f of n, this is back to problem 5, is 2 minus 3n, and f is mapping from the integers to the integers. Is f onto z? And here's my hint, and this is where you have to do a little work. Make a table of ordered pairs for the function f. Does the range of f equal z, right? In other words, do we hit everything here in the codomain? That's what it means to say the range of f is z means the arrows coming out of the domain hit everything in the codomain, right? Well, you'll be able to see whether or not that's true if you actually take the time to make a table of ordered pairs. Now, we're not going to list all of the ordered pairs in F because there are infinite number of them, right? The domain is infinite. So we have an infinite number of values that we could plug in for the integer n. So this function is actually an infinite set of ordered pairs. But what I mean when I say make a table, maybe you never did this, but maybe you did do this in your junior years when you were in secondary school. So f of n equals 2 minus 3n. So when I say make a table, we're going to put n and then we're going to put f of n, which is the f value, right? And it's 2 minus 3n, okay? We're just going to try to find some of the ordered pairs. We're not going to find them all, but we'll find some of them. Now, when we do this, let's pick easy numbers to plug in for n. We're talking about the integers, right? This is the domain. So, here's 0, 1, 2, 3, 4, -1. Like, don't go buck wild with like 99 and 157, and crazy numbers. Like, let's put in 0, 1, 2, 3, 4, -1, -2, -3, -4. Okay, we should be able to get a pretty good idea about the ordered pairs if we just look at those. Okay, so let's do this together. When we plug in 0 for n, what is f of n? What is f of 0?
2.
Yeah. So the point 0, comma 2 is a point on the graph of f. Okay, you with me?
Yeah.
All right. What's f of 1?
-1.
Nice. What's f of 2?
-4.
What's f of 3?
-7.
-7, right?
Yeah.
F of 4.
-10.
See what's going on with the y values? They're jumping. All right, what's f of -1?
-1 was that?
So -3 times -1 is +3. 2 plus 3 is,
2 plus 3, sorry, that's 5.
yep, we're going the other way now. What's f of -2?
8.
Now, wait a second. Do you see the pattern? 2, -1, -4, -3, -10. What are we jumping by? Jumps of size what?
So 2, that's 3, 3, 3,
3. So what do you think f of -3 should be without even looking at the function?
7, 7.
Should be 11, right? Let's check it. Yeah, it's 11. And f of -4 should be 2 minus 3 times -4. And it should be 3 more than this, and it is. All right, so that means the y values have jumps of size 3 between them, right?
Mhm.
Are we going to hit every single z with our y values?
It's jolted by 3.
Jumping by 3, and that's because this is called the slope of the line. Did you ever learn about the slope of a line?
Yeah, y equals mx plus b.
Yeah, it's a long, yeah, right. So y equals mx plus b. M is the slope. B is called the y-intercept. And if the slope is bigger or, in magnitude, plus or minus, bigger than 1, then we're going to be jumping some of the y values because, every third one is going to get hit, right? 2, 5, 8, 11, 14, 17. Every third value is going to get hit. So there's a whole bunch of y values that we can't hit. For example, you give me a y value you don't think we're going to hit.
Mm, Negative 1.
Yeah, we're not going to hit 1. Okay. So let's just check. Our claim is f of n is not equal to positive 1 for any integer n. I mean, it sure doesn't look like, it's not one of these, right? So how do we prove it? Prove the claim. Well, let's just assume that f of n is equal to positive 1 for some integer n, okay? Let's see what happens. Well, the function, here, f of n equals 2 minus 3n, right? That's our definition. We got to use that. So 2 minus 3n has got to equal positive 1, right? Now let's solve for n. Bring the 2 over as a negative 2. That means negative 3n equals negative 1. And that means n equals 1 over 3. And that's not an integer. So to hit positive 1, we'd have to drop in 1/3, right? Because if we drop in 1/3 here, this becomes 3 times 1/3. So this becomes 1, and 2 minus 1 is positive 1. But 1/3 is not an integer. It's not in our domain. So you're right. We're not going to hit 1 because no integer, when you multiply it by negative 3 and add 2, will give you positive 1. So you've just proven that this function is not onto because it jumps. The y values jump and they miss a bunch. 2/3 of the possible integers get jumped over. We only hit 1 in every 3. Does that make sense?
Yeah, absolutely. So this only be proven by this arithmetic. Like if you had a graph, is this is about graphs, right?
It is about graphs to some degree, but even if you just do this and you've thought about what we've thought about with sequences and you understand onto you and that the onto needs to hit every y value, right?
Mm,
In Z, you can see, oh, these are jumping by jumps of size 3, not from here to here, but if you start at -10, -7, -4, -1, 2, 5, 8, 11, 4. The point is, there's a space between the y values, even when the x values are consecutive, right? And that should help you uh, be able to see, oh, I'm not going to hit some of the Y's. Let me pick one for sure that I think I'm not going to hit. Assume that I do hit it and then show why you can't, because it would take a number that's not an integer to hit the positive 1 in the codomain. That should help you with the other parts of problem 5.
Okay, and then also, Professor, so I saw one of the announcements that said guess there were gonna be like a in-person session in YR. I forgot the.
Yeah, because that would be our normal final exam time and room. So it's free. But that's for the students that are in the 3:30 class. You're in the 2 p.m. class. Do you have a final from 3 to 5 on Thursday?
No.
Good. I hope you can make it to the in-person.
Okay, so okay, yeah, 3 to 5. Yeah, I can read.
Yeah, I'm hoping see, I know everybody from the 3:30 class can make it from 3 to 5 because that's the normally scheduled time for the final exam for that class. So I know that those kids are free. And I had a student from that class specifically ask if we could have class on Thursday. So I said, okay, I'll see if I can do it, and we can. And I'm hoping a bunch of you folks from the 2 o'clock class can also make it.
Oh,
I guess I'll find out tomorrow when I talk to students. And if there's too many students from your class at 2 o'clock that cannot be there, I'm going to try to find out if I can stay in that class a little longer, maybe till 6 or something. So the others, but I'm glad you can make it. I mean, most of the students from 2 o'clock, they never come to office hours, right? It's just you and Karen. Jessica is from the other class. And once in a great while, Alpha comes and he's from the later class at 3:30 too, as well. So, but we'll have other Zoom office hours also. If you have a time that you would like an office hour, it could even be like Thursday morning in Zoom, Friday, then please email me and make a request.
and also,
I'm going to stop recording now.
okay,